Thanks, everyone. All right, can everybody hear me even in the back? Yeah, I see nods. All right, and this is going to be an interesting talk because I'm not going to do kind of an overview of Kafka. I'm going to talk as much about stream processing as Kafka itself. So do people have like basic familiarity with Kafka? Like you've heard of it? Yeah, probably like 50%. How many people use it? How many people use it in their company in some way? Yeah, pretty good number. Cool. So what this talk is going to be about is actually kind of the intersection of two things. So two things that maybe people mostly would think don't intersect. So it's going to be about stream processing, and it's going to be about microservices. And I think probably your gut instinct is these are just like two different types of fruit, right? The one is about kind of like a real-time, MapReduce-y processing streams of data, analytics thing. The other is more like, yeah, we had this big monolithic application. We had to split it into parts, and we put some REST services in place. And so, what is this part? Hopefully, that'll be the question I'll answer. So it turned out that I actually spent a lot of time with both of these two things. So, prior to starting Confluent, which is where I work today, I was at LinkedIn, and kind of at the very same time, we were doing two things. One was splitting up a giant monolithic application into hundreds, and then, God help us, I think over 1,000 services. The other was rolling out and building Kafka and making it kind of the central backbone for streams of data. And so, I can talk a little bit about how they, interacted. And that process actually, this process of taking a monolithic application and splitting it, it actually had pretty significant pain that was associated with it. It worked eventually. So the goal, the goal of splitting into services was we would be able to scale our software engineering organization. And that happened, right? So we were able to go from a small number of engineers to well over 1,000. But the pain really came in operations. It came around latency. It came around uptime. And it came for like a really obvious reason, which was we had a bunch of applications, and they called each other in some giant graph. And as you hire more engineers, this graph of services that call each other gets split more and more, right? You're splitting services really to make people productive. So it has as much to do with the number of people you employ. And for whatever the kind of triggering request was, maybe you would go to linkedin.com, and we would need to make a homepage. And that would call out to a bunch of services that would fetch data and do different things as part of that homepage. In order for this to actually come back and give you your homepage, everything underneath would have to work, right? And at first, we did this in kind of a blocking way where we would call one thing, and then we would call another thing, and then we would call another thing. That was kind of a disaster. And eventually, we did it in a non-blocking way, so we would call things in parallel. But still, for that chunk of work to be done, everything in that graph had to complete. It had to complete successfully. It had to complete in a way that everybody understood. And that became incredibly difficult to keep working as the number of pieces went from a handful, to like 1,000, right? You can kind of think of it almost like probability. Like if you have 5 things, what's the chance one of them is going to go wrong at any given time? It's probably not too high if we all are diligent and do our jobs. If you have 1,000 pieces, there's always something breaking at any given time. And handling that complexity ended up being kind of the core challenge of making services work. And we got better at it. We got a lot of monitoring infrastructure that was really good. The service layer got really good. We got really good at building non-blocking REST services. But one of the things I think we came to realize, and it came in part because we had Kafka, and so we had another approach for building things as well, was what we were doing was building things that were synchronous, right? They might be non-blocking, but they were synchronous. This request, this homepage wasn't done until everything else underneath it was done. And yet often, the work we were doing was not synchronous. It was things that could happen in the business later, right? So if you do some action on a website and it needs to update somebody's newsfeed, that doesn't need to happen while we're making the next page for you. Those things are like disconnected. And so the lesson out of this was really to try and come up with some way to make things that were asynchronous actually asynchronous. Make things that in the business or in the world were asynchronous happen asynchronously. In other words, we wanted to be able to take some subgraph of this and make it just happen later, make it not be part of that interaction. And that's the way you actually lop off the hundreds of things that are in a given request context. That's how you actually reduce it, right? And so this became actually a kind of an important insight, and it was true there. We ended up with a lot of things that were being driven off of the Kafka stream and something that would be triggered as basically actions. And so the question is, like, how common is that? Is there a lot of parts of business that are asynchronous, that happen asynchronously? And I think the answer is yeah. Like, if you look at other businesses, I think they're actually maybe even more asynchronous. So if you look at a retail business, when you're buying something, that's like a synchronous interchange, right? I'm like, here's some money. You're like, here's a product. That's a pretty synchronous interaction. I don't really want to give you my money until I believe there's at least a promise of a product. But the rest of the business, everything else that happens, maintaining stock in distribution centers, moving that around, shipping stuff to stores, restocking and inventory management, reordering, adjusting prices, all the analytical backends, the meat of that business is all asynchronous. And that's actually not that uncommon, that there's, in any company, there's a chunk of it that happens while your customer waits that's interactive, and there's a larger kind of backend that's happening independently. And so the question becomes, OK, great. We like this idea of taking our software and splitting it into small chunks we can work on independently and deploy independently. What's the mechanism for building a service that's asynchronous? How do you do that? And so the kind of traditional answer, at least for people who have some kind of background with service-oriented architectures or anything like that, is you have a message queue, right? So you basically get a message queue. The application puts something in the queue, and the applications that need to react process that asynchronously. So does this work? Does this make something asynchronous? The answer is yeah, it kind of works. I mean, what is the message queue doing? It's basically promising to store the data until it's processed. Why is that important? Because this person can't go away until it has some promise that the work is going to be done, right? And so the message queues actually do something reasonable. But when we were trying to actually put them to work, we were trying to take kind of traditional enterprise messaging systems and put them to work in a big consumer scale website. It actually didn't work well at all for a number of reasons, right? One, message queues tend to be like one machine. So you're like basically putting your thing on one machine. If you're trying to do that in a way that scales across a large company with lots of requests, you're not going to have one machine. You're going to have lots of them. And all that interaction is very complicated. Secondly, the whole promise of this thing is basically storing your message until it's processed. And it turns out a lot of these messaging systems are like the world's worst storage systems. It's like the worst database ever made, right? So that's not great. So kind of the theory of message queuing, it kind of makes sense, but the practice was not great, especially if you look at an area like databases, where a bunch of smart people have tried to make it really good over many decades with every university in the world participating in that research. That has not happened with message queues. So our vision was a little different. We wanted something where we could actually take these streams of data where we could store them while they were being processed asynchronously, something that could both combine data coming out of relational databases, event streams coming out of applications, and it could serve both apps that would process, stream processors, as well as a data pipeline for things that needed it. This was kind of our vision of what next generation messaging would look like for us. And in LinkedIn's architecture, maybe the kind of prior state was something like this, where you have a set of request response things that all call each other. You have a bunch of relational databases that serve stuff that eventually became key value stores. You have kind of a big batch thing that rolls over once a day in the back. And then the connections between this were just kind of a mess. It was just everything kind of connected where it needed to via different ad hoc mechanisms. And what we moved to over time was something that looked like this, where you have kind of a central streaming backbone or message bus thing that connects everything. And that's the point where applications, the kind of request response domain, goes into the asynchronous domain, right? Anything published there, that's the asynchronous boundary, right? You put a message here. Applications can be triggered off those messages. They can do things. They can take some action. They can put stuff back. It also acts as a kind of feed of data for downstream systems that need stuff. So that was the role for this. And these applications, what are they doing, right? They're not just taking the message. They're actually doing something with it. They're doing some kind of processing on this stream. And that's kind of what leads me into the stream processing part of this. So I'm going to get into this. I'm going to say a little bit what I mean by stream processing, because I think most people's inclination is it's like we're going to have MapReduce, but in faster. And I think that's maybe like technically correct in some way, but like the wrong gut instinct, and it'll lead you to like think about it wrong, right? So I'm gonna make an argument that by stream processing I actually mean something more like an event-driven microservice, something that responds to a stream of events that processes it. And to kind of flesh that out, let me just go through how this compares to the things you know. So there's really kind of 3 paradigms for programming. 2 everybody's familiar with, 1 is new. I think most people are familiar with request response. This is how your REST service works. This is how this is client server. This is like JDBC. I send a request, I get back a response. I send another request, I get back another response. It is 1 input gives me 1 output. And if you do programming professionally, there's a good chance you spend your day making something that works this way, so much so that you may not even think about it as a thing. There's another weird thing about this paradigm, which is when you build a request response service, it is always there to process future requests. So that sentence doesn't really make sense. But when I start a service, it doesn't go back and process the past. It processes new requests which will be sent to it. Duh, right? Like, yeah. But actually, batch processing, the opposite, works the opposite way in both cases. So batch processing is all about processing the past data, the data that was stored from yesterday, the things that already happened, not the things currently happening now, right? And instead of taking 1 input and giving 1 output, it's going to take all the inputs, kind of churn on them, and give all the outputs. So batch processing, this is your Hadoop job. This is when you took your first computer science class, if you did, they make you write some command line thing that takes a file and filters it and spits something out. That's batch processing. And a shocking amount of the back end of big companies still runs off this. And so what's stream processing going to be? I said it wasn't quite just batch processing faster. It's going to be a little different in a couple ways. So like request response processing, stream processing is going to handle future requests. It's this infinite stream of future inputs that are coming. It's going to handle that. Like batch processing, it's going to allow you to go back and process the past. It's actually going to stitch those 2 things together. So you can go back and process old things, and you can just keep processing as new ones come. And unlike the 2 examples I gave, instead of taking 1 input and giving 1 output, or instead of taking all the inputs, which wouldn't really even make sense if you have an infinite stream of inputs coming to you, you're going to be able to take some inputs and produce some outputs, and the program will get to decide what sum means, right? And that means that you could, on one extreme, be like a request response processor, where for each thing that comes in, you produce 1 thing that goes out. But you could also be like a batch thing, where you take really a lot of input before you produce any output. Or you could be somewhere in between. And that somewhere in between is what's going to give you control over the latency that output comes with. It's going to give you a lot of control and generalize these 2 areas. So stream processing, instead of being kind of a weird niche thing, is going to be actually kind of a generalization of these 2 ideas. And to emphasize this, what I don't mean is something that's kind of transient or approximate or lossy. So if you ever hear about streaming algorithms, they usually mean something like this. I actually just mean a data system that's going to process both the past and the future stream of requests that will be unbounded in size. I don't mean it will get the wrong answer. And in this example I gave, you can see kind of the streams if you squint. And I think this is true about most companies. If you kind of squint at what a company does, there's some kind of inputs and there's some state machine of processing happening and some outputs of what the company does. If you look at this retail example, there's these kind of stream of sales, shipments of products, and then you have some processing that's occurring where you're saying, OK, we're selling out of this, we should reorder. We're selling out of this, we should raise the price. We're not selling any of this, we should lower the price. There's a whole back-end streams of like analytics, the reordering events of, hey, get me this, that would all occur in reaction to that. And so I think this idea of viewing a company as a set of streams connected by processing is actually kind of powerful. All right, so that's what stream processing is. What does that have to do with Apache Kafka, which I also put on the subject of the slide? Let me try and say. So I showed this picture. I said, we wanted something that would connect different data systems that would allow us to build applications that would respond to streams of events. And that something was basically Apache Kafka. That was the motivation for that system. And Kafka, I'm going to give like a super brief sketch for the third of the audience that isn't super familiar. What it is, you can think of it as being kind of like a next generation messaging system, although it works very differently. Fundamentally, the thing it's keeping track of is a stream of events or records or messages. I'm going to use those words kind of interchangeably just because people do and you can't make them stop. A message for us is going to be a timestamp when it happened. It's going to be a key and a value. The key and values in Kafka are just byte arrays. You would probably have some kind of higher level representation that would have lots of subfields in your value. It would probably be a rich record. It could be JSON. Basically, it doesn't matter for the purpose of this talk. This is what the fundamental thing in Kafka is streams of these records or events or messages. And Kafka will organize these into a log, or into many logs. And what a log is just a sequence of records, right? So it's like a commit log. I don't mean a log like the request log for Apache where it logs out to some text file. I mean like a binary file that stores the records that were appended. So always new writes getting written to Kafka are being appended to the end of this log, right? The first write is here. Each of these little boxes is meant to represent one of those records that I talked about. Each record is given a unique number, which is called the offset. And that's kind of the point in time that that record happened. So lots of different applications could all be writing at the same time, and they would just be appending to the end of this log. And you can read this log. There can be many readers, each at some point in time reading it. So you could have 0 readers for this stream of messages being appended, or you could have many, and each reader can be at a different point in the log. So kind of not that crazy. It's actually a very simple structure. Turns out to be a good basis for publish-subscribe messaging. So inside of many distributed databases, you would basically see this style of structure being used to distribute messages within the cluster. It's usually kind of an implementation detail. Inside a lot of databases, you would see something like this. But basically, in messaging terminology, you would call the writer a producer and the readers consumers. And if you made them separate processes, now you have publish-subscribe messaging. So this is the fundamental data structure in Kafka. It turns out this is really important for stream processing. So stream processing, I said we were going to be able to kind of unify with batch processing a little bit, right? So how does that work? If I have a log of messages like this, it's clear I can process this in many ways, right? The reader controls where they're at. So you could have a reader which starts at the beginning, runs to what the current end is, stops, and is done. That's basically a batch processor, right? You could also have a reader which is kind of an incremental batch processor where it wakes up, it processes everything that's there so far, it produces some output, it goes to sleep, it wakes up the next day, it processes the new stuff, it goes back to sleep. You can also have something which is very real time, which is basically subscribing to things as they come in and processing things as they occur, right? And so the key thing is we can have one data structure, one view of our data, which includes both past stored data, new stuff coming in as reality happens. We can unify all those in a single way. So the logic you write that processes, the system that does processing, it doesn't change whether you're talking about the past or the present or the future things that haven't happened. And a particular important application of these types of logs where you would see them all over is in databases. So if you've heard of like the MySQL bin log, usually, unless you're like a DBA, it might just be something that's like currently hurting you. Like, oh, we had some problems with bin log replication. Like under the cover, a lot of databases are basically keeping a log like this. And they're using it to replicate the sequence of updates that occur. And this is common in distributed databases. It's common in relational databases. So you have some kind of source system, which is basically keeping a log of the modifications. And those can be replicated out to derived databases, which just apply those changes, right? And so these replica databases are going to be in sync with this, but maybe just a little bit behind. They may not be quite caught up, but they'll go through the exact same sequence of changes. So this mechanism has been around forever. And this support for replicating a log of changes is actually very core. Kafka has built-in special support for this type of semantics of logs. And in Kafka, the primary data structure is called a topic. That's basically a feed of events. That's a stream. It's basically just a partitioned set of logs. So for people who already knew Kafka, that was probably boring. For people who didn't raise their hand before, that was probably not enough information. But it'll set up the rest of what I'm going to talk about. So Kafka basically has 4 APIs that let you deal with this type of stuff. It has a producer, which I kind of talked about, which is allowing you to basically write and append to these logs. It has a consumer, which allows you to read. So you can read, usually you would read from left to right, from old to new. But you could always go back and read again if you need to, which turns out to be very important. It has a connect API, which allows you to kind of suck data out of existing systems or write it into existing systems. So it's kind of like the opposite in the push-pull dynamics. And then it has a Streams API. And the Streams API is what's allowing you to do processing on streams. And that's what I'm going to talk about for the rest of this talk. This is relatively new. It's about maybe 9 months old-ish. So in this picture I showed, I said, well, we want to be able to have applications or stream processors that somehow react to the stream of things that are happening. Maybe they're taking changes that are happening in relational databases and transforming them in some way. Maybe they're reacting to streams of events published by apps. And they are outputting some kind of derived stream. So this is kind of what the Streams API was motivated by. Let me kind of go through the state in the absence of this, of how we saw people doing it. And I'll talk a little bit about how we were motivated to build this API. So the first thing we saw people doing was kind of bare bones processing of streams of messages. They were basically using Kafka like a messaging system. There was a way to produce and consume. And so we kind of called this like hipster stream processing, because it's like kind of back to basics. You don't need much. Hipsters, since this is San Francisco, everybody knows, but they're going to favor the more primitive tool, right? So if it's a bike without gears. If it's a computer, it's actually a typewriter. If it's a PDA, I think it's like a little pocket full of cards on paper with a fountain pen. The nice thing is those tools actually work pretty well. They're not complicated. They don't fail in complicated ways. If you've ever written a fixie, the chain doesn't come off as much. And that's actually true for this approach to processing as well. So what people were doing is that you write an app. You basically consume some stream. You do something with that stream of data. And maybe you produce back some kind of derived stream. And so this is a way where, without any particular support in Kafka for processing, you can actually do stream processing. And the only problem is, a little bit like the fixie bike, you kind of eventually come to a hill. And then it's like, oh, this is why we have gears. And so the hard parts in the hills in stream processing are going to be a lot of questions around state. So what happens if every input produces some kind of derived output in my output stream? That's easy. But what if I need to count things over a window of time? And what even is time? If I have stuff that's happening in the past that's combining with things that are happening in the future, what does it mean? What am I even using as the clock that's deriving time? And how do I chop that up into windows I can process? And then what do I do if I change my code and I need to go back and recalculate my results in some way? Maybe I've made some kind of fraud detection application. I've detected a set of fraudulent people. When I change my rules that calculate fraud, I need to recalculate the set of fraudulent people. How do I do that? And then a bunch about how does this work when it scales out? What are the semantics? How does fault tolerance work? These are kind of the hard problems. And as you see people kind of dive in with these problems, they would sometimes get these right, but they would often get them wrong. That's kind of the definition of a hard problem, is you don't necessarily get it right on the first try. So the other approach for stream processing with Kafka is there's a whole bunch of frameworks that do something kind of like MapReduce on streams in some way. So there's Spark has a way to do stream processing, kind of by dividing up the stream into little batches and processing them. There's a system, Storm. We had built one at LinkedIn called SAMSA. Flink is something newer. They're all to varying degrees attempting to do this. And the challenge we saw with a lot of these was just they were relatively complex when you actually looked at the full set of things you would need. So if your idea was, hey, we want to take our big monolithic application, we want to split it into chunks, we want some of these to be asynchronous, and we want to use stream processing to build the asynchronous ones, you can't introduce that much complexity before you just fall over and die, right? The whole point was you're trying to make it easy and agile for people to work. And the kind of standard stack for a lot of stream processing things was something like Kafka, which would fork off data, some kind of distributed stream processing framework that would really deploy your code. So maybe you would write a Storm job and you would deploy it into a Storm cluster. Maybe you would have some kind of separate distributed database for keeping track of any kind of state that would occur. So if you're doing counts, if you're joining data together, anything that covers more than a single row. You probably need some kind of database that's output is going to. And then finally, your app would work with that. And then, if you ever want to be able to go back and kind of recalculate things, or if there's any kind of inaccuracies in this flow, maybe you would have a whole batch system that would do the same thing. So sometimes this would, some variations, at least on this, would be called the Lambda architecture. So maybe you would run some kind of daily batch job that would recalculate things. You would kind of re-implement your code there, or try and have that span in some way, and you would produce output for that. And so this works, people do it, but kind of if you look at this and you say, OK, yeah, we have all these services, we want to migrate a bunch to this, it's just going to be relatively complicated, right? So our primary goal in the Streams API was to try and simplify it and make stream processing into something that could be a mainstream approach to application development that's simple enough to build and run things and carry a pager for them without wanting to hang yourself. So we basically like this picture. We just want to give you more convenient ways of processing the streams of data. So the key operations that the Streams API is going to give you, everybody who has used Scala would be familiar with them. They're kind of the things you would see in something like a Scala collections library. I guess lots of languages have something like this, where you're able to chain lots of operators together and perform some kind of transformation on the data you have. So what's different? Why wouldn't you just use the Scala Collections API? We're really trying to do a couple of things. So first of all, the scope is now going to be across many instances of your application. So obviously, if you have a collection in Scala, it is just you wouldn't even think of it. But of course, that collection exists in memory, probably on a single machine, almost certainly, right? Our definition of a collection is going to be across a pool of machines, right? When you call map, that mapping is going to happen across many instances of the application. Secondly, the collections are all unbounded in length, right? So the list has no end. And so you have to have very careful, you have to be very careful with a lot of the operations you would take for granted, where you call size on a collection, right? If it's an infinite collection and your approach to calculating the size is to traverse and count, that's going to be a slow operation. So the core operations are going to be something like map, which you take an input stream, you transform it in some way, and you produce an output stream. Filter, you take an input stream, you get rid of some stuff. Aggregate, you take an input stream and you combine records in some way, counting, summing, et cetera. And join, where you're either joining two streams together or you're joining side information to a stream of events. So these are kind of our core concepts. There's a bunch of variations on these. A Kafka Streams program, I'm going to show an example. This is Java code. There's basically some configuration and setup, the actual logic, and then the end. The logic is doing, this is Java code, by the way, so apologies, but that was the screenshot I had. The Java code is basically doing word count, right? And it's doing word count on a stream of documents. It's taking them, it's splitting them up by some white space thing. It's counting the number of occurrences of each word it sees. And then it's outputting that to some output topic in Kafka, right? So what's kind of interesting or new about this? What's new about it is you're able to, first of all, nobody cares about counting words, but you're required, if you have any kind of big data system, to give an example that involves counting words. So what does this do for you? How does it help you? Well, basically what it's allowing you to do is take this and run it over many instances of the application. The individual application is nothing fancy. Like you can notice, this is just a main method. So it's just invoking this library, which is allowing it to coordinate what work it's supposed to do and what work the other instances of the application that are currently running need to do. And if one of those instances dies, it's going to take over some work. And if one of the a new instance comes, it's going to donate some work for it to do. So it's handling that coordination. This is not different than what the Kafka consumer itself would do, but it's doing it in a way that actually handles the semantics of transforming data. That's it. That's it. So the kind of hard problems are basically that, like how do you split up the work? And then how do you manage this state that is computed off the stream, particularly if that state gets large. So if you are counting the number of words and there are many words, you need to be able to spill out of memory and do that effectively. So what you get is basically something that kind of in the world of stream processing is actually a cutting edge stream processing system. It has kind of the set of features you would expect, but it operates as a simple library. And there's 3 core simplifications I'll highlight. So the first of these is that we're basically using Kafka. So what do I mean by that? I mean, it's basically all the same concepts that you would have in the stream itself. So the data model is the same. It's these key value pairs with timestamps. That offset, which controls what you have and haven't processed, your position in the stream, is the same concept. The management of back pressure comes from Kafka itself. The management of scaling out this processor comes from the same group management feature that Kafka consumers use. All the management of state and partitioning is the same. So from the point of view of the Kafka cluster, anybody using this Streams API, it's just like another application using a producer and consumer. But we've handled a lot of these harder problems for you. And in particular, the reprocessing capabilities. If you write an app and you need to kind of go back and recalculate your state off of the old data, that's very easy. You basically just rewind it in time, and you process the stream essentially in fast forward. Right? So normally stream processing, you would think of it as processing the current state. If you have, in my fraud example I gave earlier, you have some current set of fraudulent people. If you change your code that calculates that, how do you get the new set? Well, you just rewind and process reality very quickly. You could temporarily scale out and have more instances while you're calculating that if you want to. The handling of time is built in, and it uses Kafka's concept of time, the offset marking your position and the timestamp captured with the message. And this will do true event time. So even if data arrives late from mobile devices, from other data centers, whatever, it will be calculated correctly off the time of the event. The next simplification is basically you don't need a cluster. So this application uses a library, and it acts like a producer and consumer in Kafka does. You need the Kafka cluster, but you don't need any kind of like stream processing cluster. It's not like you set up some kind of magical Kafka Streams daemon. You don't launch your code into that. Everything about how your code is packaged, configured, deployed, that's just totally up to you. It's however you do that with other services. So I think that's really important. Anybody who has ever used one of these frameworks that starts to take over the actual deployment of code for you, and a lot of these frameworks do, it seems simple at first. The example always looks simple, but then you realize that whoever deploys your code actually dictates a lot about how it works. And so it becomes, it's like you kind of meet somebody, you go on a first date, and they're redecorating your apartment right away. It's a little bit like that where, I ran into this with all the Hadoop frameworks where it's going to end up dictating a lot about how configuration works, the life cycle of your code, everything about how you program, deploy, and do things. That's really not ideal. So I think a big advantage of this is basically you start and stop and deploy programs the way you normally do. All this framework does is handle the scaling out of processing and contracting and handling failures and the stream stuff. That means, of course, this works with the full deployment coolness spectrum. So whether you are basically syncing your code out onto servers via some shell scripts, or you're using something like super cool like Kubernetes, either will work with this framework. Like basically, it doesn't matter. We don't do that part of it. The final simplification has to do with actually supporting operating both on streams of data, but also tables. So tables of current state. Why would you care about that? Well, I gave this retail example. In this example, there was a stream of sales. There was a stream of shipments. But there's a current state that you're calculating off that, which might be your inventory on hand. And in order to decide when you need to adjust the price or when you need to reorder, you need both. You need your inventory on hand, and you need to know what's selling right now, right? And this is actually very common, this kind of current state. And we've done this in a very principled way and made it a first-class citizen of these APIs to handle that. And so I gave this example of database replication. A really cool example of this table facility is the ability to take a stream of changes out of one or more relational databases, materialize it into some kind of view in your app, and basically keep an up-to-date materialized cache or view of things that are happening elsewhere in the company that come together. So an example of that might be something like you have many slivers of information about your customer split across many services and databases, producing the kind of universal customer profile or customer 360 view or whatever you want to call it. That's an example of this. And that state in this latest release can actually even be queried. So that unified view, you could replicate it into an external database, but you could also query directly the application and just check its current state. And of course, I talked briefly about the Connect API, which allows you to run connectors to other data systems. This will work in concert with that. So if you think about ETL in the data warehouse space, in some sense, the extraction of data and the loading of data into other data systems is happening with this Connect API. The T, or transformation, is kind of the Streams API. And so that's how all those pieces fit together in this streaming platform vision. What we've been doing at Confluent is basically trying to package a bunch of those things together into a distribution that lets people get started. So we produce a distribution of Kafka that basically has all the clients for different languages, has like REST access for things, has connectors to common data systems off the shelf, has some management tools, has management for schemas and the compatibility of data. And that's it. I think I'm almost out of time, but maybe I can take a few questions. Question? Cool. Yeah.
So is Streams growing into something more like Flink then that's going to be doing the compute processing and accessing data for state and memory and things like that?
Yeah, I mean,
what will be a difference, I guess?
That's right. So I think at a high level, yeah, both of those things are things which allow you to process streams of data. In implementation, it's quite different, I think, because basically what we're giving you is more a library or API rather than a kind of code execution framework. So maybe the use cases are a little different because of that. But yeah, they're both allowing you to do processing on streams of data. So in that respect, they're very similar.
So when would I pick, Kafka Streams over Flink?
Yeah.
If I got problem X, I mean, what are the
That's right. So the question is all about what's the difference between Flink and Kafka Streams, or perhaps any other stream processing layer. I mean, they all work, right? So there's a whole ecosystem of things that will kind of run on top of Kafka. What we're trying to do is give something that is very simple out of the box that's part of the Kafka cluster. So where I think that is most appropriate is for use cases which are kind of in this core business logic or service area. I would say that's probably a little different from the kind of analytics space where maybe you're building kind of a something that could have been a batch MapReduce job, but you want it to run faster. I've just seen the teams that work on that stuff, it's usually different. The way you manage that code is usually different. Where I think we shine is basically, with the Streams API is probably, areas where you are, maintaining that like a service you want to deploy. The advantage of this approach is basically you deploy it on your own machines, whatever they are. You totally own the lifecycle of that code. There's no kind of shared processing cluster you have to deploy into. Your only dependency is basically Kafka. Next question.
I was wondering if you could say a little bit about the two concepts of the table and the stream. When you go from a table to a stream, I can kind of imagine like three semantics. Like two of them are very closely related. One would be like, here's the latest value that has been written to this table. The second one, which I would think is strictly better, is here's the latest value and the previous value for that key that was written. And the third one, I think a lot of people actually want, but doesn't seem very convenient, is the ability to occasionally scan the entire table periodically, some way of programmatically saying, okay, actually I want to do something that's not just an update-oriented thing. Can you say just something about that and what your thoughts are about it?
Yeah. So the question is all about, more about tables. What are the semantics of them? Yeah, this is a super deep area. There's probably a whole talk just on that. The semantics in Kafka are, of the three versions, it's the first. So what you can basically think of a stream as having data, and the semantics of that are kind of in the eye of the beholder. So let's say I have a stream and it represents customer profiles or customer account information, right? And every time you change your account, I'm basically posting to that stream the new customer account. There's two different ways I could represent that. I can treat it as a stream, and if I count records on that stream, I'm going to get the count of customer account changes, right? So maybe if I count by geography, I would get something like customer account changes by geography. If I treat it like a table, I'm actually going to be computing this on some derived thing which represents like the current state, right? What is the current customer profile for each customer? What's the current customer account? If I count on that, I'm going to get like how many customers do I have in California, not how many customer changes. And the difference between those two is kind of in the eyes of the beholder. You might want one, you might want the other. So we've given you kind of a flexible view of that. In Kafka, there's a whole set of features that do log compaction and stuff in the background to make this work. But the key ability is you can take things which are maybe the master data is in a database, a relational database. You can capture changes out of that, which is like, oh, here's the new value of it. You can process that in a way that makes sense. Or you can have a stream of something which is a pure event, like, hey, we had somebody click on this. Off of the we had somebody click on this, which is a pure stream, you can compute a table of the number of clicks per hour per user or something. And you can process that table incrementally as well. So what you can think of this as, as being is the ability to compute something derived off of a table, like a table in a relational database, but keep that up to date incrementally. Coming back to your original question, why do you use the latest state instead of one of the other variations? The answer is actually because A, that unifies it with the other concept of stream, so the records look the same. B, most systems will only give you that. I do agree it's useful often to have the prior state, but you can get that by maintaining it in your stream processor, if that makes sense. So if you want it, you pay. If you don't have to. The reason you pay is because you have to keep the old thing, and not everybody has that. And so it's better to have you pay downstream than require it upstream, since many people can't do that. Other questions?
I'm afraid we'll have to.
OK, well, I'll take anything offline. Thanks, everyone.
Thanks, Jake.